Okay, hi guys. Okay, today we are going to talk about turning effects of forces again, and we are going to part 5.3 to talk about center of gravity. Okay, so at the end of this section, okay, you should be able to explain what is meant by the center of gravity of a body. Alright, now, so based on the video just now, based on your everyday experiences, okay, you know that you will have to actually balance a ruler right at the middle point over there, right? Okay, so why do we say that we need to balance it right at the middle point over there? Because at this point over here, we say that this is the center of gravity of the ruler. So what does center of gravity mean? It means that this is the point where the entire weight of the ruler appears to act. It is as though the weight of the ruler is acting downwards at this point over here. So if you actually place your finger at that point over here, and if the weight is acting downwards, you will see that since the weight is exactly at the pivot, there is no turning effect due to the weight of the ruler. Right, so we've covered this. Okay, why is it that the uniform meter rule balance only at the 15 centimeter mark? Right, so why is that? Is because at the 50 centimeter mark over here, right, this is where the entire weight of the object appears to act. This is the center of gravity, and we say that the weight of the ruler will act through the center of gravity. So if you place the pivot, okay, slightly to the left, the weight which acts through this center of gravity will contribute to a clockwise moment, right? So therefore your ruler cannot balance anymore, okay, it will topple. But if you were to place your pivot exactly at the 15 cm mark over here, just above the center of gravity, then the weight which acts through the ruler over here will be directly on the pivot. So there will not be any moment due to the weight of the ruler. So we say that the moment of the weight W is 0. The moment due to the weight of the ruler is 0. Okay, so the weight doesn't contribute to any turning effect. So the ruler will remain balanced. Okay, so the official scientific definition will be this. Okay, the center of gravity of an object is defined as the point through which its whole weight appears to act for any orientation of the object. Okay, so what does it mean for any orientation of the object? It means that, for example, if you have a ruler like this, right? Where is the center of gravity? Right there, right smack in the middle over here, right? Now, if you were to turn your ruler in this direction, right? Where is the center of gravity? It's still right there, smack in the middle, like that. Okay, if you were to slant your ruler like that, where is the center of gravity? That will be the center of gravity, right? So at all 3 points over here, okay, at all 3 orientation, okay, so we call this orientation, right? At all 3 orientation over here, the center of gravity remains the same. It doesn't change. So when we say the center of gravity of an object is defined as the point through which its whole weight appears to act for any orientation of the object, right? Okay, now what about the weight? How will the weight act then? So for point number 1, the weight will act downwards like that, right? At number 3, the weight will act downwards like that. And for number 2, the weight will act downwards like that, right? So the weight will always act downwards, okay, towards the center of the earth, okay, but the center of gravity still remains at that point. Alright, so let's take another example over here, right? Okay, so where do you think the center of gravity of this man will be, right? Okay, so the man, this is where his mass is being distributed at, right? So for him to balance like that, his center of gravity is roughly over here, right? Okay, roughly over here, right? Or maybe slightly lower, okay? So this is the center of gravity. So this is the point where the weight of the man will appear to act, right? So this will be the point where his weight acts. Now, if the man were to actually move slightly to the left, right? If he were to move slightly to the left, then his center of gravity will also shift to the left, right? Okay, let's say he moves slightly to the left, right? And then the center of gravity shifts to the left like that, right? And because the center of gravity shifts to the left, it contributes to a turning effect, which causes the man to topple, right? But at this position, you see that the CG is directly above the pivot. So the weight acts through the pivot like that, right? So there is no turning effect due to the weight of the man. Alright, so let's take a look at center of gravity of some regular shape objects. Okay, so regular shape objects will be, for example, like your rectangle. Okay, the center of gravity will be directly in the middle, right? Okay, for your triangle, the center of gravity can be found by finding the midpoint or the intersection point when your triangle, the top one, okay, divides the bottom one into two equal parts. The top one divides the bottom one into two equal parts, right? And the top corner here divides the bottom here into into two equal parts, right? Okay, and then the intersection of these 3 points, this is where your center of gravity will be, right? Okay, so short form of center of gravity, sometimes we will just write it as CG, okay? Okay, and then for a cuboid, okay, you will be right in the middle over there. Okay, for a ring, okay, this is the part which is interesting. Okay, for a circle, okay, so if this is a normal circle, like a disc, right, like your frisbee like that, right, the center of gravity is right smack in the middle there. Okay, so this is pretty straightforward. Okay, but in a ring, okay, the interesting thing is that the center of gravity is still in the middle over here, right, because the center of gravity is the point where the weight appears to act. Alright, so even in empty space like that, right, it is as though, okay, the weight of this entire ring is acting through this middle part of the ring over here. Alright, now to illustrate that point again, right, okay, so let's take a look at this guy, right? Okay, so for this guy over here, this is where his body is at, right? Okay, so if we want to take a look at the center of gravity of this guy, okay, where would it be? Okay, actually the center of gravity of the guy is somewhere over here, right? This is where the mass of the body is distributed in such a way such that at this point over here, this is where you have the center of gravity. This is the point where the weight appears to act. So if I were to draw the force drawing over here of the weight, you see that the weight is acting directly above the pivot, right? So that's why the man will not topple over. He will still remain he will still remain balanced. Okay, he will not topple over, he will still remain balanced, alright? Okay, right. Now we are going to do a very quick experiment, okay, to see what will happen if I were to release a book and pivot my pivot the corners of the book over here. Alright, what do you think will happen? Okay, why do you think the book is in this orientation? Okay, so these are the questions that we want to ask ourselves, right? So let's take a look at the video. Okay, so I let go of the book and yeah, okay, so the book fell and it actually remained in this position at the end, right? Okay, so let's take a look at that more closely, right? In the beginning, okay, in the beginning, okay, what do you notice? Okay, you notice that my finger here is exerting a force in this direction, right? So it's exerting a force in this direction. Okay, this book over here is what we call a regular size object. So the center of gravity will be somewhere in the middle. Okay, somewhere here. Okay, somewhere in the middle over here, right? So this center of gravity, the weight will act downwards. And since this is my pivot, right, this part is my pivot, this weight which acts through the center of gravity will contribute to a anti-clockwise moment, right? Then this force over here, due to my finger over here, you can see my finger there, this will contribute to a clockwise moment, right? So what did we learn in the previous portion, right? The previous lesson, we said that when the total clockwise moment is equals to the total anti-clockwise moment, the object will be in equilibrium. Equilibrium means it will be balanced, right? Okay, so this is exactly what happened. Okay, in the beginning it's like that. And then now I release the finger, right? So there is no more clockwise moment. So the weight which acts through the center of gravity over here, right? The weight which acts through the center of gravity over here contributes to an anti-clockwise moment, right? So the object will turn, right? Or the book will turn, right? So no more clockwise moment, only anti-clockwise moment, right? Okay, and then finally, when I just let it remain there, why does it finally come to a rest in this position, right? It finally comes to rest in this position because, let's take a look, okay. So the center of gravity is somewhere over here, somewhere in the middle, right? This is the CG. The CG is acting down, sorry, the weight is acting downwards over here, right? So the CG is in the middle, the weight is acting downwards, right? And since this weight is acting through the pivot like that, right? So the weight is acting through the pivot like that. There is no perpendicular distance to the pivot anymore, right? In the previous example, there is a perpendicular distance. Where is the perpendicular distance? This is the pivot, right? This is the line of action of the force, right? The perpendicular distance is there. This is the perpendicular distance, right? So there will be a moment, there will be a turning effect, and it will be an anti-clockwise moment. What about this example again? The line of action of the force is here. It runs through the pivot point over here, and so therefore there is no perpendicular distance, and therefore the weight which acts through the center of gravity does not contribute to a turning effect, right? So no turning effect, and therefore the object will be in equilibrium, right? So there's no turning effect, so it's in equilibrium. So it's in equilibrium either when there is no turning effect at all, or when the sum of clockwise moments is equal to the sum of anti-clockwise moments. Okay, so either one of this. All right. All right. So now we are coming to the next part. Okay, normally for this activity, I would very much like to bring you all to the lab. Okay, but because we can't, I will just have to show it to you from here and show a few videos to illustrate my point. Right? Okay, so basically when you have an irregularly shaped object, that means an object which is not like a rectangle or a circle, and you find it very difficult to find exactly where the center of gravity is, you can actually use this method, okay, to find the center of gravity of an object, right? Okay, so first and foremost, okay, if you have an irregular shaped object like that, right, what you need to do is you need to make 3 tiny holes, okay, at the corners at different location of the cardboard, right? Okay, and then what you do is set up a retort stand like that, put a needle over here, put a cork over here, a needle through the cork, place a plumb line over here. Okay, so basically a plumb line is just something like a pendulum. Okay, you can use a pendulum, or you can use anything which has a string plus a weight at the bottom over here, right? So at the bottom over here. So you can use a pendulum bob also, right? Okay, so ensure that the cardboard can swing freely about the pivot, right? So this is your pivot point. Okay, so basically this is the front view. Okay, this is the pivot point. What you do is let this object swing for a while. Okay, once it comes to a stop, okay, what you do is mark out this point over here. Okay, you do the same. Okay, you do the same for all the 3 holes, right? And then at a point of intersection, okay, at the point of intersection of these 3 lines over here, so you can have one over here, right? And then you repeat the same thing with this one over here, and then you repeat the same thing with this one over here. At a point of intersection of the line, that's when you will be able to get the center of gravity of the cardboard. Okay, now it's very difficult for you to visualize just from me saying this. Okay, so I'm going to actually show 2 videos to you to illustrate this point to you better.